So in many different kinds of programming platform, it's useful when you can create functions, methods, and those functions can help human do something efficiently. And when you have multiple methods for the similar purpose, you can put them together as a class. For example, I can have a class for calculus, and I can define all kinds of functions inside this calculus class. So in the future, when you import this class, you can use the methods being created inside the class. So today we are going to learn how to create a class of different methods. Okay, so in this particular example at the bottom, you can see the way to define it in Python is as follows. You start with class and the name of the class. Then colon, second line, you need to have indentation, then define. So we already learned how to use define to create functions. Basically, here you are doing the same thing. You are defining your own functions, and we sometimes call them methods. The methods inside this class. In this particular case, in this slide, we use those as examples. We can have differential, differentiate, and integral. Okay, so maybe you have some inputs for the derivative, and you have some inputs for the integral. And what's inside this function will be defined below the definition. Okay? And the bottom right here is like how you use it. In the main code, you can say, okay, perhaps you have a variable called answer equals to, so focus on here. The way we use the method is going to be following so-called the object-oriented programming. So in object-oriented programming, computer treat all kinds of items as objects. So a class is an object, and underneath the class you have method. It's another object. So how do I use the method inside the class? You can use the name of the class, and over here you have a dot. You put a dot right there, and then you follow with the dot, you give the name of the method. And then do what's necessary for the method. So the dot helps you to realize you are calling one method inside this class. So whenever you have a dot, this is object-oriented programming. Okay, so Python has object-oriented programming as well. So over here, in this example, calculus dot, no space, calculus dot, and the name of the method, differential, and then define the input based on how you define the function right here. Okay, so you can, now we get to learn how to create a class like this. Okay, so let's go to Python and start to build some simple examples. So let's say I'm building a class. Maybe I will call it my math. Okay, column. Inside my math, I'm going to define, for example, sum, and I will say x and y. Okay, and inside x and y, I will say z equals to x plus y. And then I will return z. Okay? And then I will define another one, for example, minus. Maybe I should call add. I should name it add, and then minus. So x and y. It's a very simple example. Z equals to x minus y. Return z. And maybe define multiply. I just use mult. So x and y. Z equals to x times y. Return z. Define divide x and y, and z equals to let's do x over y. So return z. So now from outside, I'm going to use it. So I will just say, for example, x equals to 1, y equals to 2, and then z1 equals to add x and y. For example, oh, sorry, I should say my math dot add, okay. And then run it. You can tell z1 can be computed like this. Let me try what if we do this. If you make y as a floating number, in this code, it doesn't matter if you are having integer or floating number, they all work. So integer plus a floating number equals to a floating number. So at the end, z1 is a floating number, right? So you can try more. My math, very simple example. Okay, x and y, z3, my math, multiply xy, z4, my math, divide x and y. So at the end, you cannot do divide. Oh, typo, divide. Yeah. So 1 over 2.5 is 0.4. Yeah. Now you know how to build your own class. So please try to build a class and build some methods inside. You don't need to follow exactly what I did. You can let's just practice it. Okay? If you have no idea what you want to do, you can try this one. So let's try to build a class with multiple methods and write some main code underneath. So, by the way, let's monitor how Python runs the code. If you go to the debug mode and then stop at the first line, let's see how Python runs this whole thing. So in the debug mode, first, when Python jumps into this code, it realizes, okay, it's a class. And then we are moving forward. And you realize Python will go through the whole thing and did nothing because it's like registering everything into the system, but doesn't need to do anything yet. Now the line goes to the main code. And when I start with line 15, we start to get some numbers based on your definition inside the memory. So now I have capital X and capital Y. So over here, if I click this bottom, it will directly run that line but doesn't jump into it. So let's try that once. Okay, so after this line is completed, Z1 was created. But in the second trial, I'm using the other bottom, which will jump into whatever that's inside the code to see how Python goes through the entire script. So I'm using the third bottom in the debugging mode. I'm clicking it. Then you realize Python understands this is a method minus inside class my math. So it directly jumps to line 5 where I define the method minus. Then you can now move one line forward. You will realize in Python it generates two more variables. They are local variables for the method right here, small x and small y, and I created a small z right here. So x, y, and z were generated after we jump into the method, and then they are local variables. So once we obtain z, this return z will send the result back to the original line. So let's move forward and see what happened. That line was completed. After this return z, Python code jumps back to the original main code and then move forward. And then we got z2. So if you monitor how Python runs the script in what kind of sequence, you will be able to understand more what happened inside Python, and that helps you to understand how you should write your code. Okay? So that's basically what happened. This is why we want to have our class definition before the main code. We want the Python code to run through the definition of class first, kind of like registering those functions inside the memory, then go to the main code. Whenever our method is being used, Python will jump into that method and create local variables for that calculation. Once the local calculation is completed, it jumps out of the local script, goes back to the main code, and the result will be sent back to here. Okay? So please try to build a class. Okay, I see most of you can do this very effectively, it's not very difficult. Okay, so if you still need some time, I will keep it on the right hand side of my screen, and I'm hold on. So you still have the right hand side of the monitor to follow. Okay.
这礼拜。看到了吗？好，对啊。
learn something and then in 1 second. Okay. Thank you. Okay. So I was trying something about the next part. So inside the class, there are some predefined functions that was created by Python, and those methods were designed in a certain way, and you have to follow those names. If you use those names, Python understands what's going on. And these are 4 examples. So they are unique functions only for Python. And for all kinds of class you build, you can use those special methods. And Python understands what those functions are for. So the reason why they create those methods in this way is because usually you don't define functions in a name like this. Starts with 2 underlines and a specific name and 2 more underlines afterward. So in the next page, I'm going to introduce something called init, basically initialize. And for initialize, it allows you to have internal variable, like local variables, inside initialize. Okay, so in this particular example, it's too small. Let me enlarge. So what you can do is you can have a class, and you can define initialization for one of your method, and you want to create something called self. It's like a local variable only when you initialize the function. Okay, so over here in this particular example, it's memorizing a name called Brian. Okay, and this self.name becomes like an internal variable inside this class, and you can use it anytime in other places. And over here, when this function is called, my class initial is called, this part of the function will be executed first. So the initialization part will be run first. Then it will go to the method that you specify right here. And if you have this special function with self right here, you can actually use the internal variable that you defined earlier inside initialization. So I made one example right here. I created this initialization where I will print this is my math, just to show the user, okay, you are running this code. But this initialization won't be run all the time. It will be run when you put brackets after my math. So this is quite unique. You have to put brackets after my math, then it will go to initialization. Okay? So you are let me show you from the debug mode. Let's run the code slowly to realize what happened. So first, when in my math class, the first thing it does is to go through all the functions you created So it's going to go through all the functions you create to understand what are the what are the methods you prepare. Okay? And then starting from the main code, we already know what happened earlier. I clicked the wrong, sorry, do it again. I made the wrong click. Here. Okay, so we already know what happened earlier. At this point, the screen doesn't show anything. Okay? Which means we never jump into initialization yet. Only the last line where I say my math, and I put the brackets right here with empty, nothing inside. That means you want to go to this initialization. So let's jump in and see how the Python code runs. When you jump in, it directly, I specify add s just to, I should use a different name. I should say add with print. Okay, maybe it's a more reasonable name. So sorry, let me run the code again, and then debug. So here I use a different method called add print. So when you say add print, you want to not only compute x plus y, you also want to print something. So over here I'm printing the answer is, and I convert the result z to string and then put them together. Okay, so let's see how the Python code goes inside the script. So here I step into the function. First, because of math bracket, it will execute the initialization right here. And then first line is it will print this is my math. So run that part. On the screen you will see this is my math. And then we define something called self.name. So it's a internal variable, and the variable it's defined based on object-oriented programming. It's a object called name inside this variable self. So self is in red color, and you have to use specifically self as internal variables. So inside this internal variable, there's an object you created called name. So self.name is the object you saved inside this self object, and the content is the answer is. Now we continue with the code. You realize once this initialization is completed, it jumps to the method you specified. And since we already created self.name, so you can use this internal variable inside add print. However, from outside, you don't really need to specify self, because self is an internal variable. However, the one student just reminded me self has to be the first one. Yeah, I did it wrong. Self, I place it in the last, but self has to be the first one. Okay, so self is like a hidden variable, only the class knows. For the user, you don't even really need to specify self. And then capital X will be direct to small x, and capital Y is directed to small y in this code. Then let's jump in and see what happened. So inside this add print code, we have our local variable x and y coming from outside, the capital X and Y, and we have this self object, which was created when we initialize it. So we run this math, So we have a local z, and we print. So when you are printing, since we already defined self.name, then we are able to print the answer is 3.5 on the monitor. So the answer is, this phrase was prepared inside this initialization process. So if you have something like this, you don't need to repeat all these for each command. You can reuse it if you define another function called minus, but this time print. So here I say self x and y, and inside I'm doing z equals to x minus y, and this time I can print the result, self.name, and then z6 equals to my math dot minus print x and y. Okay, so I really need to convert it into string here. Okay, so for this one, run the code. You can see my answer is minus negative 1.5. So whatever that was inside initialization can be used. What if I do this? Okay. Then you have to say my math bracket. Otherwise, self was not. Let's see what happened in Python in the debug mode. Okay. For if my math doesn't have the bracket, let's see what happened. I will jump into the code. Let's see. Jump into the code. Then there's nothing to. There's no self right here, so it has to be running this part. So you have a self created. Okay, because right here when I try, let me try something else right here. Let's see what happens. Should be divide. Jump into the code. Yes, this part is fine. Oh, jump up. Jump up. Okay, so you cannot mix use. You cannot mix use the code without self with the ones that has self. Okay, you cannot mix use. So if you really need the internal variable, you have to define in this way. And if you try to mix the usage that we had earlier with initialization, it gives you the number of variables is different, so it won't be cannot be done correctly. Okay, so over here we created two different kinds of ways to define methods. First, we don't even have initialization. We just do something and then return the result. Do some math and then return the result. But in the different second kind of way to define the methods, we make good use of this initialization, where we can have initial variables, the self variables, like the internal variables. So we can use it for our methods. Okay. So over here, the way to execute them is it has to be like this. You have to say my math bracket. So this bracket allows Python to understand you have to go to this initialization process. So over here, it runs this part. Then inside this add print function, this self object is being properly defined, was properly defined. Okay? So I want this to be clear, so maybe I erase multiply and divide. So you can visualize, you can see, visualize them in the same screen. Okay? So let's try to create this initialize function and then try to use those self variables inside the methods. And here are my example on the screen. You can follow me or you can try it by yourself. You can try your own process or own method. So this part is a little different from what you learned in the past. So if you have questions, you may, the TA can come help. Okay? So this part, we want to try initialize for your Python code. Please make sure you are able to successfully use it. Okay, I just quickly add one more. Earlier I was creating self.name, which is a string. You can also say self.something, which is a number. Here I have an integer 3. So over here so it's like a hidden number inside the code. I define it as that, as 3. As the user, you don't know what's s, right? So here I have a function add s. I will give a number to this method and ask this method to add s to the number that I provide. So it will perform x plus s, which is the number I created from the initialization part, and then print results. So over here, in the new part, you will see the result. I gave the code 1 because I said add s. I put capital S into the code. Capital X was 1, and over here, basically it's performing 1 plus some secret number inside initialization, which is 3. So at the end, the answer is 4 because 1 was the input I provide, 3 was the number inside the initialization. Okay, so it's up there. Maybe I close one more part so that you can see everything. Yeah. Now you can see what I did in one shot. For initialization, you can create objects, internal variables, which is a number, and you can use it inside your method. Over here, I used self.s, which is the number 3. I also used self.name, which is the string. The answer is. I use both of them in this particular one. Okay? So try them. Okay, so please make sure you successfully try this. Okay, so if you have tried to create initialization, let me show you another thing. For this particular class you created, you actually don't have to have this definition of your class in front of your main code. You can save this file as a Python code that is basically for the definition of your class. So over here, you can get rid of the main code right here and save it. By the way, you don't want to erase what you had earlier. You want to keep it somewhere else. So don't do anything yet. I already pasted what I had earlier in the second file. We will do that. Okay, so for the first file that we did, I want you to save as a specific name. For myself, I save this file as my underline math underline py. So I save this particular file as a specific file for the definition of the class. And in a separate file, I'm going to say from my math py, meaning I'm going to find this specific Python code where a class was defined. And I'm gonna say import my math. So when you say import my math, that means you are going to import the class that was created in that specific file. So in this particular code, you can directly use all the methods that you created in my math. So if I run the code right here, you can see, let me clear the memory. Okay, remove everything, and then let me run the code. Trying to get rid of this. Anyway, so from here you can tell the method that you created from this class can be used in this particular file. So why don't you try it? So I'm going to keep it here. Okay? So why don't you try to have a separate file where you call the Python code that you created for your class. So in your class, you just define your class. You don't need to have your main code. Your main code could be outside. Okay? if you successfully try this, you can also try this, where you say from this particular Python file, import the particular class, and you say as capital N. So in this main code, you can use this short name, capital N, as to represent the class. So that's another way to make your code shorter. Okay, so please also try this. Either I'm gonna repeat what I did, but you are not supposed to write them twice. So I'm just duplicating them in one screen so you can understand there's a difference between them. Okay, so you can import a class, and inside your main code you use the name of the class. Or you want to make it shorter, you can import the class and then say as something short. So in your main code, that short name represents the class you imported from this particular file. Okay? So please try it. Okay, so you guys keep trying, and let me prepare an exercise for you. Okay, I just created an interesting math problem. I hope it won't be too difficult. We are engineers, mechanical engineers. We should be solving engineering problems. So now let's try to build a class to perform Taylor expansion. Okay, if you still memorize Taylor expansion. So now we have a function. Some function we are going to estimate later on. And the Taylor expansion for that function can be obtained by f of the expansion point plus x minus the expansion point times f first order derivative, substituting the expansion point, and then plus 0.5 times x minus the expansion point squared times f second order derivative, substituting the expansion point. So what is the function? The function could be sine, cosine, whatever, but for that specific function, we need to define it. So inside the class, let's prepare a math function. For example, it's sine x. So later on, when we put a number x here, it will give me sine x. Okay? So you may ask, so what's the purpose of this Taylor expansion? So we already know it's sine x. Why we need Taylor expansion? Sometimes we just want to have specific function values that is not in the same form. Okay, sometimes you need polynomials. The result of this will be polynomials, second order polynomials. Anyway, we're not in calculus. This is just practicing Python to solve an engineering problem. Okay, I will guide you through in Python, but just let me explain what this problem is about. Okay, so if we have a function where whenever we have some f, but whenever we have f, that means you go to this method and then get a value back. But how about f prime? This time we don't want to define f prime. We want to estimate the f prime by something called finite difference. Here is finite difference. So you can estimate f prime by f x plus delta minus f of x over delta. This is called finite difference. Let's try it. But what is delta? Delta is a small number. We will define delta later on. And what is f over here? F basically is your sine. So whenever your Taylor expansion needs this, you need to go to finite difference code here. And then when you need f, you go to your function to get f. Okay? How about f double prime? Here is the estimation for f double prime, also by finite difference. It's gonna be f x plus delta minus 2 times of f of x plus f of x minus delta. The whole thing divided by square of delta. Okay, that will give you estimation of f double prime. But from here you can see many times you need the value of delta. So let's define delta inside the initialization. So you only need to define delta once. Okay? Then in the main code, the purpose of having Taylor expansion is to estimate the function type, function shape, based on specific expansion point. So in the main code, you will ask the user to provide an expansion point, basically x0. So x0 is a user provided value. And then for the main code, whenever you see x0, that's the number you provide to Python code. And we haven't talked about how to plot a function. So I decided to ask you to show the function values from 1 to 10. So basically, you will compute f1, f2 until f10. So whenever you compute f1, you print it out. And what does 1 mean? 1 means you plug in, I should say f of x here. One means you want to see what's the value of f of 1. So 1 will be here, here, and here, right? And x0 is some expansion point value you provide. So those are here, here, whenever you see x0. That's where you have your expansion point value. And then this code should be able to execute estimation of f1 to f10 and then give you some numbers. And that numbers won't be exactly sine x, it's a second order approximation of sine x. Okay, so if you sample this function with a lot of points, at the end you have a quadratic function. Okay? So let's try it. I'm gonna post this on Facebook so you will be able to get this screenshot. Okay. So TA is going to post this on Facebook. So when I program on Python, I won't be showing this slide. And if you need this slide, you can check our Facebook. Okay? And let me show you how this can be done. You can challenge yourself. See if you can get this. And I give you a lot of freedom for defining the names and variables. You don't need to be exactly following what I'm doing here.
列成可以。立着可以吗？传给你，看，好好看。
if it works, it looks like this. But I need to double check if it's right or not. Let me see whether it's right or not. The sine function looks like this. The Taylor expansion at 0. Okay, let me try just first order. First order. I'm not sure if it's right or not. Sine, let's try this. Looks like a linear function. Sine comes like this. So if I approximate sine 90 degree, if I have expansion point at 90 degree, 90 degree would be 1.570795. Something must be wrong. My code must be wrong. Okay, I typed it wrong. 1.570795. No, it's weird. Doesn't look like it's right. Something somewhere is wrong. Taylor extension. Finite difference. Plus minus this. Self delta. Or maybe the delta is not small enough. Try this. So 1.570795. So weird. I'm not sure if it's right or not. Let me try a quadratic function, maybe. Otherwise, I'm not sure if it's right or not. Continue to what you're doing. Let me just make sure it's right. It's weird. It's weird. Why? Second order time expansion. Oh, yeah, it works. Okay, it was right. So the curve was sine function, and the blue curve is the Taylor expansion. So from here you can tell it made pretty good estimation of the shape of the sine function. Okay, it was right. Yeah. If I have more terms, I can have even greater even more accurate approximation. But I think a second order is already good enough. Okay? So you don't need to plot everything. I just want to show you what I did. In order to show everything on one screen, let me squeeze these a little bit so you can see it. Let me explain my code. You don't need to follow exactly. The first one was to import math because I need a sine function. I want to approximate a sine function. So in math, there is already a function of sine. And I use matplot. This is just for plotting purpose. It's not introduced completely yet, but I used matplot library and pyplot, and over here I define a short name capital P for pyplot. Oh, this is the main code. So I call this class as Taylor for Taylor expansion. For the initialization process, I define a small number self.d. D represents delta. I give a small number, okay? And then I define a function called func. So func is my function. Inside func, I basically use math.sine. So I use math.sine to give me values for psi. Okay? df represents first order derivative of the function. Inside, I basically perform so-called finite difference. I compute the function value with a small increment of delta, x plus delta, minus the function value with the x without delta. X plus delta, f of x plus delta minus f of x divided by delta. That's basically the approximation of derivative, right? And then I return the value. Now ddf represents second order derivative, where I perform finite difference again. Over here, function value of x plus delta minus 2 times f of x plus f of x minus delta. This is the central scheme of finite difference. Divided by delta squared. So I divide it by delta twice. Then I return the value. Now, the Taylor series. Basically, function value at the expansion point plus your x minus expansion point times derivative computed at the expansion point plus 1/2 times x minus x0 square times second order derivative computed at the expansion point. So basically, I program this exactly like the math, follow the math. Then let's focus on the main code. For the main code, I define a capital X0. I want this to be a floating number, otherwise in the code, the accuracy won't be good. Then I use input to ask the user to give expansion point. So you can give any number, that will be the expansion point for the approximation. Over here, capital Y and Z are just for plotting. I built a list of Y and a list of Z. Whenever I compute, I just keep them in those two lists. The first list was to keep the values from Taylor series. The second list was to keep the value for the true function. So I can plot the true function and also I can plot the Taylor series. And here is just to print. In fact, I can just write here, say y. Because I already, no, not y. I better not do this. Because the last y, yeah. But let me just do this to avoid troubles. Okay, so from x range from 1 to 10, you know the last one won't be count. I print f of whatever x I have equals to whatever Taylor series gives me. And for the Taylor series, I put the x value into it, and then I put the expansion point into it. So the first variable is the position that you are estimating function value. So which will be one over the value from 1 to 10. x0 is the expansion point that you provided to computer when you see the input. The rest is just for plotting. I use pyplot to plot out the function y and the list of y and z and then show. So as a result, if I have an expansion point of 0.5 or some other, for example 4, okay, and I will see function value of 1 to 10 Those are Taylor series estimations, Taylor series estimations evaluated at positions of 1 to 10 based on the expansion point 4. And if you show the plot, you will see the polynomial was the generation based on the Taylor series. And you can see this polynomial becomes quite accurate at the position 4 because the expansion point was 4. But the polynomial was not accurate somewhere else, anywhere else. Okay, so that's basically what Taylor series is for. It estimates a nonlinear function as a second order equation, second order polynomial. And it's only accurate at the expansion point. Okay? So that's basically my interpretation, and then you can try it. Okay? So by the end of today, please show a code like this. If you have no idea what to do, you can follow what I did. So basically, just copy mine and then type in to try it. So at the end, I just need to see the display of F1 to F10. You don't need to do pie plot. You can just to show whether your code is right, or just show the F1 to F10. That's fine. Okay, so before you leave, please try this. You can either try it on your own, or you can just follow what I did. My code was not perfect. At some positions, I didn't program in the most effective way, but it works. Okay? Now you try it. So if you're done, you can raise your hand, and then you can go. Questions? Or you're done? You're done. TA, someone is done. So if you copy my code, that's okay. It's just a practice for today. But I want you to go back home and read what I did, understand what happened. Okay? Many of you probably learned this for the first time, and when you try to use it to solve a real engineering problem, how do you use it? That's the main purpose of this course. You need to be able to know how to use it. Okay? So try to learn from my demonstration. This one cannot be used. Why? Because of this. But we never self here. So if we call self from here, this self has to be here. Sometimes it's hard to understand the logic. Why they program like this way. But anyway.
不是我不知道答案。废话，我完全抄不出来。完全正确。
按算什么都没有是吧？
不知道。
啊？
不知道。
不要想，为什么？
我不知道啊。你问我。
你打错了。
啊？哪里错？
还有两个positional argument。
完全照抄哎。
确定吗？你有抄对吗？
有没有抄的？
那怎么没有跑出来？
抄错了吗？
哪个抄？那个近视在。哦，你说红色？
来，我来检查一下。
只有那个。因为你这边你选的，我都没有，跟我不一样，你也是善，我打都是善，为什么我们？看起来是一样的。这一次剪好，你的近视错，再跑一次。谢谢。就是说它这个叫那个有限差分，这个是要加的，这个是加delta，这个要减。那如果你两个都交 delta 的话，那不就是跟一样的，所以你就变成还是一次微分，就会错。
好，谢谢啊。
快，帮我看进很快。我知道抄，
我知道了。你看，名字太小。
烂呐。
数学断面读到这里。
妈的，动力。
他就没有去培训。
靠啊！
靠啊！哎。轻轻松松。
这个按钮。
这个是错的。哦，因为我打针。OK，就好意思，不好意思。对啊，太大。
Everyone OK？ So are you able to think of this code if this is a if this is an exam? Yeah. So in